Have you ever wondered about the mysterious pattern of prime numbers? Why do these numbers, divisible only by 1 in themselves, seem to appear in such a seemingly random distribution? These are the questions that have fascinated mathematicians for centuries. Prime numbers, those unique figures that stand as the building blocks of the number system, have an allure that is hard to resist. Their distribution, seemingly random yet crucially important, has been the subject of intense scrutiny and endless fascination. From the ancient Greeks to the modern mathematicians, the allure of prime numbers lies in their fundamental nature. They are the atoms of arithmetic, the indivisible entities from which all other numbers are built. Yet their distribution remains a mystery, a riddle wrapped in an enigma. One mathematician, Bernhard Riemann, proposed a hypothesis in 1859 that has since become one of the most famous unsolved problems in mathematics, the Riemann Hypothesis. This hypothesis, involving the distribution of these enigmatic numbers, has challenged and enticed mathematicians for over 160 years. So what exactly is this Riemann hypothesis? In simple terms, it's a prediction about the distribution of prime numbers. Imagine you're walking along a beach picking up seashells. Some are small, others are big, and they're scattered randomly along the shoreline. This is a lot like how prime numbers, those unique numbers that can only be divided by 1 in themselves, appear on the number line. They seem to pop up haphazardly with no apparent pattern. But Bernhard Riemann in 1859 proposed there might be a hidden order to this seeming chaos. Riemann's hypothesis is like a treasure map, pointing to where we might expect to find these prime seashells. It's based around something called the Riemann zeta function, a complex mathematical formula. But let's not get tangled up in that. Instead, think of it like a magical lens that lets us peer into the world of prime numbers and predict where they might be hiding. Riemann suggested that the zeros or solutions of his zeta function, much like coordinates on our treasure map, would all fall on a certain line, known as the critical line. This line, if it exists, would give us a deep insight into the pattern of prime numbers. But here's the catch. While we've checked the first few trillion solutions and they do indeed fall on this line, we can't prove that this will always be the case. It's like seeing seashells scattered along the beach and guessing they'll continue in the same way but not being entirely sure. And why does this matter? Well, prime numbers are the building blocks of mathematics. They're used in everything from cryptography to quantum mechanics. Understanding their distribution could open up new avenues in these fields and beyond. In essence, the Riemann hypothesis is a conjecture about the pattern hidden within the seeming randomness of prime numbers. Solving this hypothesis could lead to a deeper understanding of the very fabric of mathematics. Why has this hypothesis held the attention of mathematicians for over 160 years? Well, it's not just because of the $1 million prize offered by the Clay Mathematics Institute. The allure of the Riemann hypothesis lies in its profound implications on the understanding of the universe of numbers. If proven, it would unravel the enigma of primes, the building blocks of numbers, and their mysterious distribution. The hypothesis also has significant connections to other areas of mathematics, intertwining with quantum physics and the behavior of chaotic systems, thus opening doors to potential breakthroughs across multiple disciplines. The $1 million prize from the Clay Mathematics Institute only underscores the significance of this hypothesis. But money aside, the real lure is the intellectual journey. Solving the Riemann hypothesis would be akin to finding a Rosetta Stone for mathematics, deciphering the deepest secrets of numbers. The Riemann hypothesis is more than a mathematical problem, it's a quest for understanding the deepest secrets of numbers. So, what have we learned about the Riemann hypothesis today? Well, we've delved into the enigma of prime numbers, and how their distribution forms the core of this hypothesis. We've learned that Bernhard Riemann proposed this theory back in the mid-19th century, a hypothesis that, despite being over 160 years old, remains an unresolved riddle. We've explored how the Riemann hypothesis is more than just an academic curiosity. It's a cornerstone of mathematics, influencing fields as diverse as quantum physics and cryptography. We've also discovered that it's one of the 7 Millennium Problems, identified by the Clay Mathematics Institute. This means that if you can prove it, you'll not only secure your place in mathematical history, but you'll also be $1 million richer. The Riemann hypothesis remains one of the greatest unsolved mysteries in mathematics. Who knows, maybe you could be the one to solve it.